SwayamPrabha. Digital India. Educated India.
Hello everyone. So in the last class we ended by talking about the conservation of energy and how the energy was getting transferred from the large scales to the small scales. So if you remember, what happened was we split up the energy into the filtered energy, into the kinetic energy associated with the filtered velocities and the residual kinetic energy. And the residual kinetic energy, we are defining it as half times u dot u bar minus half u bar dot u bar. Okay, and EF is the kinetic energy associated with the filtered velocity field, so that would be just half u bar dot u bar. Now, the idea of doing like this is so that when we derive an equation for EF given by just taking the filtered momentum equation and multiplying it by uj bar, then we get a transport equation of UF that looks like this. And if you notice here, so the leftmost term is the rate of change of EF, isn't it? The d dt of EF. So while the leftmost term is the rate of change of EF with respect to time, obviously as a material derivative, and the second term on the left hand side is this transport term. It turns out it becomes a transport term. And the right hand side, we are reserving it for either a source or a sink term, and we are calling it epsilon F and PR. Now this epsilon F turns out it would be 2 nu Sij bar and PR would be minus tau ij superscript r Sij bar. So these are the source and sink terms. Now these are obtained, I had discussed this in last class, if you actually take uj multiplied by the filtered momentum equation, and what happens is this is what happens, right? I had shown this last class. So when you multiply the uj by each term in here, and then you use the chain rule to separate it as these two terms in the derivative, then you end up getting terms that look like this. Now this is easily identified as a transport term because of the del xi derivative on the outside, and everything else can be the source and the sink term. Now the epsilon f, which is 2 nu Sij bar, this is going to be, it looks like a dissipation, right? It looks like a dissipation, but think about this. We are choosing the filter width in the inertial subrange. In the inertial subrange, viscosity is not playing as much of a role. So dissipation is going to be negligible. So we can safely say that epsilon f is going to be almost zero, is going to be negligible. Then there is a matter of PR, which is minus tau ij superscript r Sij bar. Now this one here can be a sink term in the equation for EF and will be a source term in the equation for Kr. So what is it? It is the rate at which energy is being transferred from the large scales to the small scales. It is essentially a transfer term. Now if the dissipation is not present in the inertial range, and because viscosity does not play a role, then once the energy gets transferred from the large scales to the small scales, then you have dissipation at the small scales, which you are not taking care of in LES. That is true, but you can now say that PR would be approximately equal to epsilon. The epsilon, in the true sense, the dissipation that is active in the dissipation range at the small scales, what we consider in the DNS, what we do not consider in the LES. So that's what we are saying. PR is approximately equal to epsilon. So that takes us to now defining the Smagorinsky model and deriving an equation for it, because we know what the subgrid scale stress term is now. We need to model that, isn't it? Because in order to close it out eventually, we need a subgrid scale model, and we pick the Smagorinsky model here because it is one of the most widely used model, a very popular model that is used out there. What we are discussing here today is the classical version of the Smagorinsky model and not what is called the more modern and more widely used version of the Smagorinsky model called the dynamic Smagorinsky model. I'll discuss the differences as well as we derive these equations, but I am discussing here the classical version of the Smagorinsky model. So in order to close the equations for the filtered velocity, what we need is a model for the anisotropic stress tensor, isn't it? The tau ij superscript small r. Because remember, we had split it into an isotropic and an anisotropic part. The isotropic part, we lumped it into pressure, whereas the anisotropic part is left as such because we only need to model that. So tau ij small r, superscript small r, is the anisotropic part. We need to close this equation out. So the simplest model that is available out there is the Smagorinsky model. This model can be viewed in two parts. So earlier when we did the Reynolds equations, we looked at an intrinsic and a specific assumption. In the same way, we are looking at the assumption here in two different parts. The first part is the linear eddy viscosity model. So this is our intrinsic assumption, meaning the residual stress tensor, the anisotropic part of the residual stress tensor, we are saying is proportional to the filtered strain rate. Remember, in Reynolds equations, we said it was proportional to the mean strain rate because that is what was available. We are solving the steady state equations. The mean strain rate is what is available. Here in LES, we are solving the filtered conservation equations. So the filtered strain rate is available. So tau ij small r is minus 2 nu r Sij bar. So this is the filtered strain rate. The constant of proportionality, just like in the Reynolds equations, is again what we call an eddy viscosity, except this is like a residual eddy viscosity and also called a turbulent eddy viscosity. So we are referring to it as nu r. So minus 2 nu r Sij bar. So you have tau ij r is minus 2 nu r Sij bar, and this nu r is the eddy viscosity. Fine. Now the more specific assumption is that nu r is equal to, and we are using the mixing length hypothesis here, where we are equating it to the square of some kind of a mixing length, and we are calling it Ls squared times the characteristic rate of strain, so S bar, isn't it? And this mixing length, we are saying it is proportional to the filter width. So we are saying that Ls is equal to Cs times delta. So Ls is proportional to delta, or Ls is equal to Cs times delta. Cs is a Smagorinsky coefficient. It turns out the standard value of the Smagorinsky coefficient is 0.17, and we will actually derive that in today's class. But Ls is equal to Cs times delta. S bar here is the characteristic filtered rate of strain. So nu r we are saying is Ls squared times S bar, and that is Cs times delta squared times S bar. Okay. Now, according to the eddy viscosity model, the rate of transfer of energy from the large scales to the small scales, isn't it, PR as we called it, is minus tau ijr Sij bar, and instead of tau ijr, isn't it, instead of tau ijr, I am substituting this. So I get minus 2 nu r, and there would be a minus on the outside, so it becomes plus. So 2 nu r Sij bar Sij bar. And this right here, okay, is S squared, S bar squared divided by 2. Why? Because that is how the magnitude of a tensor is defined anyway. The S bar is 2 Sij bar mean, right? Isn't it? So, and square root of that, sorry. Yeah, square root of that. So essentially, this becomes nu r S bar squared. So for the Smagorinsky model, this energy transfer is everywhere from the filtered motions to the residual motions. It is one way. Goes from the large scales to the small scales, not the other way around. So according to the Smagorinsky model, there is no backscatter. There is no way that it can consider backscatter. Why do I say that? Because if you think about nu r, it is Ls squared times S bar. or Cs times delta squared times S bar. Now think about it. Cs is a number. Cs squared is going to be positive. Delta is going to be positive. Delta squared is positive. Okay. S bar is again a positive number because it is the magnitude of a tensor. So it is again a positive number. Nu r is going to be positive because of that. If nu r is positive and it is negative on the right hand side of the equation, that means you have a negative term on the right hand side of the equation. So it is always dissipation. It is always energy going from the large scales to the small scales, not the other way around. If you wanted it to be the other way around, your Cs squared had to be negative. That means when we calculate Cs squared itself, it should be negative, because Cs calculated cannot be Cs. Even if Cs is negative, Cs squared would be positive. So we have to calculate Cs squared in such a way that it can be negative. Now this is what is accomplished in the dynamic version of the Smagorinsky model, which we do not discuss in this class. But in the dynamic version of the Smagorinsky model, we derive an equation for Cs squared, which could be negative depending on the situation. Some examples where you could have backscatter are stratified flows, magnetohydrodynamic flows, where the flow stretches in one direction and the small scales become larger and larger. That means there is an energy transfer from the small scales to the large scales. It is during those situations that the dynamic version of the Smagorinsky model will be more accurate, because the classical version of the Smagorinsky model assumes that there is no backscatter, whereas there are actual flows where there is a source term, especially. So equations where there is a source term like the buoyancy term, we never discussed that in this class. We never considered the Navier-Stokes equations with a buoyancy source term on the right hand side. It could be the buoyancy source term, it could be the Lorentz force source term like you have in the magnetohydrodynamic equations, the buoyancy source term that you have in stratified equations, so on and so forth. So those are examples where you could have backscatter, you could have energy going from the small scales to the large scales, and in those cases the classical version of the Smagorinsky model is not going to give good results because it does not consider backscatter. So now that you have that, you know what the expression for the eddy viscosity is, you know where the Smagorinsky coefficient comes in. Now the question is, what is Cs, right? What is Cs? I earlier mentioned that it would be about 0.17, but how do we get that? So it is good, it is informative now to study the Smagorinsky model applied to high Reynolds number turbulence. And we know that we are choosing the filter width in such a way that it is in the inertial subrange. That means it is between LEI and LDI, isn't it? LEI is the energy demarcation length scale, that is between demarcating the energy containing range and the universal equilibrium range, and LDI is the dissipation range demarcation length scale, demarcating the inertial subrange and the dissipation range. Okay, so your delta is between that. Now, if for all these cases we are considering that epsilon s that we had seen earlier, we are considering that to be negligible, and we now know that the transfer term, as in the transfer of energy from the large scales to the small scales, that would be equal to dissipation at the small scales, or at the dissipation range. So epsilon is approximately equal to P of R. We are equating that, and PR, which is the transfer term, is now we know is nu r L bar squared, and the average of that, isn't it? We are taking average in time. So this is now equal to Ls squared times S bar cube, because nu r is Ls squared times S bar. So this now becomes Ls squared, that can be taken out because it is a constant, and then you have a S bar cube average, isn't it? S bar cube average. So using the estimate of S bar squared that we had derived earlier from the Kolmogorov spectrum, and I'll show you that a second. It comes right about here, right? The S bar squared is AF C epsilon to the 2/3 and delta to the minus 5/3. Also note this equation where I defined what AF is, which is 2 0 to infinity kappa delta to the 1/3 G of kappa squared delta d kappa. Okay, so now let's see what we get from here. isn't it? We were here, and I will have to derive this out. So I will have to write this out. So what I do is, I know that S bar squared, okay, is CAF epsilon to the 2/3 delta to the minus 4/3, isn't it? So from here, epsilon is S bar squared, okay, divided by CAF delta to the minus 4/3, this whole thing to the minus 3/2. I'm sorry, plus 3/2. That's what I have, which is going to be equal to, so I'll just split this out and write it as 1 over CAF, so C to the 3/2, AF to the 3/2, and I will write this as delta to the negative 2. Then I have S bar squared to the 3/2. I just split it. Okay. We know that LS squared is epsilon over S bar cube average, as you had seen here. LS squared is epsilon over S bar cube. Now what I do is I just substitute it in here. So then LS squared is going to be equal to, I will have this C to the 3/2, AF to the 3/2, delta to the minus 2, and then I have S bar squared to the 3/2, S bar cube. Okay, I'm sorry, so this needs to be an average, S bar squared average 3/2 divided by S bar cube. Yeah, that's it. Okay, so LS is going to be equal to, I will have delta coming up on top, and then CAF to the 3/4, and then I have S bar squared to the 3/2 divided by S bar cube. Okay, this whole thing to the half, isn't it? So essentially that is what I have here. LS is equal to delta over CAF to the 3/4 and S bar cube, S bar squared to the 3/2, the whole thing to the half. Now here is where I make an approximation. I am going to assume that S bar squared to the 3/2 is this approximately equal to S bar cube average. Let's say I make the assumption that S bar squared average to the 3/2. It is not going to be equal. We are making the assumption that they are approximately the same. So because you are taking an average and then taking a 3/2, then raising it to the power of 3/2. It's not going to be the same as S bar cube average. No, but we are making the approximation that it is S bar cube average. In that case, this would cancel out and you would just get 1 there. So then LS would be equal to delta over CAF to the 3/4. Where does that leave us? We still don't know what AF is, isn't it? So that's what we end up getting here, where you get delta over CAF. Now the question is, what is AF? Because C, we know C is the Kolmogorov spectrum constant, which comes out to be 1.5, universal constant. So we know that value. Now the question is, what is going to be AF? So we need to derive what AF is. So AF, if you remember the equation that I had shown earlier, AF is integral 0 to infinity 2 kappa delta to the 1/3 G of kappa squared delta d kappa, isn't it? Now we know that we are choosing the filter width such that it ends at the cutoff wave number. So we don't need to integrate to infinity. We can just have 0 to kappa c. Okay, 0 to kappa c. And what I do is I can combine all this kappa delta to the 1/3, G of kappa squared and D of kappa delta. So my new variable is kappa delta, and I have kappa delta to the 1/3. Now remember, we are choosing a sharp spectral filter here. So this is equal to 1 for kappa less than kappa c, and it is equal to 0 for kappa greater than kappa c. In which case, because it's a sharp spectral filter, right? You're cutting it off at kappa c. So that means your integral now becomes kappa c 2 kappa delta to the 1/3 d of kappa delta. Now you can just integrate this and it becomes kappa delta to the 4/3 divided by 4/3 multiplied by 2. And if you remember, r going from 0 to kappa c. Okay, so if you're going from 0 to kappa c, remember that kappa c is pi over delta as we had defined it. So this becomes just kappa becomes kappa c delta becomes pi. So you essentially have 3/2 pi to the 4/3. That is what you have for AF. AF is 3/2 pi to the 4/3. Now if I substitute that here, then I will have pi to the 4/3, isn't it? 3/2 pi to the 4/3. So I would have, so LS is this one. So I am trying to find out what CS is, isn't it? So that is LS over delta. So that would be equal to 1 over C AF to the 3/4. And what is my AF is 3/2 pi to the 4/3. So that would be 1 over C 3/2 pi to the 4/3. Okay, so that would be 1 over C, and there would actually be a C times 3, and it would be a 3/4, and then I would have a 1 over pi. So essentially I'm getting 2 over 3C to the 3/4 times 1 over pi. That's what I end up getting. Look at this. So CS is LS over delta, which is 1 over pi, 2 over 3C to the 3/4. Turns out if I plug in my C value as 1.5 universal constant and pi as 3.14, I get it to be approximately 0.17. So that is where the CS value comes from, assuming your filter width is at the inertial subrange. Is it the inertial subrange? And one other assumption we made is this minor assumption where we assumed this S bar cube average is S bar squared to the 3/2. So we assumed those to be equal. Once you do that, okay, you are integrating only till the cutoff wave number. So you are saying that your filter width is in the inertial subrange. You are saying there is no dissipation there. You are assuming the Kolmogorov spectrum. So the Kolmogorov spectrum in the inertial subrange is already defined. C epsilon to the 2/3, kappa to the 4/3. So then your C value is 1.5 in the inertial subrange. Based on all that, your CS value is 0.17. Now this works for high Reynolds number turbulence. Obviously anything that we have discussed so far works for high Reynolds number turbulence. And that is what we are saying, that our filter width is in the inertial subrange. So from these scalings, what we understand is that now that you got a CS value of 0.17, a constant, we are saying that LS basically scales with delta, because LS is 0.17 times delta. So LS scales with delta. If LS scales with delta, S bar also scales with delta. So S bar, the characteristic filtered rate of strain, is epsilon to the 1/3, delta to the minus 2/3. Scalings of other quantities can also be deduced. Nu R is LS squared times S bar, isn't it? So that is epsilon to the 1/3, delta to the 4/3. And so the residual stresses as well, tau ij superscript r, which is LS squared times S bar squared. That again becomes epsilon to the 2/3, delta to the 2/3. So based on this scaling, every quantity essentially scales with filter width. We kind of knew this conceptually. Here we have proved it mathematically. The other thing we have proved is the value of Smagorinsky coefficient. We are saying it is a universal value because we assumed a universal spectrum in the inertial subrange. Our filter width, we chose it to be in the inertial subrange. C value was universal. So it makes sense that eventually your Smagorinsky constant will also be a universal value, and that indeed we are getting it to be 0.17. So any computational model that you see out there, this is the standard CS value that is used. And this is for the classical version of the Smagorinsky model. The dynamic version of the Smagorinsky model does not have this constant specified. It is calculated based on other equations. So you would think that that version of the Smagorinsky model is more powerful or is more accurate than the classical version. So now that the Smagorinsky model has been derived, we can now substitute it into the filter Navier-Stokes equations, and your equations are closed. You derive an equation for U bar. So in the next class, what we'll do is we will look at some limiting behaviors of LES and close it out. Thank you.